This conference will
There's
now be
my
recorded.
So welcome everyone to another OCP Tab session. This is the 76th session, and we have Dr. Anwar going to give us a talk about secure timing architecture for untrusted edge systems. As usual, we start with a quick bio about Dr. Anwar. Dr. Anwar directs the Emerging Embedded Technologies Lab at the University of Massachusetts Amherst. Her disciplinary research looks into designing trustworthy, time-aware, situational-aware, intelligent, and fair systems for distributed and resource-constrained edge, specifically for emerging embedded application and mixed reality, wearable and autonomous technologies. Prior to joining UMass, she was a PhD candidate at UCLA in electrical and computer engineering, advised by Professor Mani Srivastava. Her dissertation focused on a new perspective of quality of time in designing cyber-physical systems. Dr. Anwar has a lasting commitment toward increasing participation of diverse group in computing. She routinely volunteers for outreach events at the university's level, such as Investigators Program, Massenburg STEM Institute, Turing Summer School, Cybersecurity Institute, and gives back to the broader community through programming for Amherst Girl Scout, Los Angeles Computing Circle, and Engineering Day for Girls. So with no further ado, we give the floor to Dr. Anwar. So let's see, the slides work again.
thank you. Can you see the slides and can you hear me?
No, I think the slides disappeared. Let's try again.
Oh, you cannot see them?
No.
Okay, why did they disappear? Um,
Try again.
can you see them again?
Yes.
Okay, so just checking in. Everybody can see the slides and hear me now.
Yes.
Okay, let's start. Thank you so much for the introduction. If I would have known that you're going to use the introduction for introducing me, I would have provided a shorter version of it.
That's fine.
Um, but thank you anyways. Um, so today I'm going to talk about security of time. It is going to be sort of a high level talk for motivational purposes, but then I will dive into one very specific topic, which is currently mature enough to talk about. There are many other directions under the theme of secure timing too, and I'll give a hint of those, as in how everything comes together. But if anyone is interested in the details of the other topics, they are more than welcome to contact me via email. Okay, so I'm going to start talking about what edge systems are, why are they untrusted, and then what kind of timing attacks are possible on those untrusted edge systems, what are the consequences of those attacks, and then I'll present one technique um, out of three major tasks that I do under secure timing to solve some of the problems. Okay, start off, what is edge? There are so many different terms that I use, so it's important to be on the same page as to what is the meaning of these terms. So this is how I imagine a generalized edge platform. You always have hardware underneath, which is passing the information to some sort of system software. It could be operating system, it could be bare metal system libraries, and then that information is passed on to the application. And this information flow happens through the OS between hardware and application. That's how we envision an edge platform. But that edge platform does not work standalone. It's part of a bigger network where it communicates or interacts with the other edge platforms through the network fabric, and it also communicates communicates with the services that are provided on the cloud, again through the network fabric. So this networked edge system is multi-tier, which means that you will find devices at different tier of this network. Some are extremely at the edge, some are at one hop on top, and then at the very top you always have a cloud, all interconnected by a network fabric. And then the edge, networked edge, is also multimodal, which means that you do not have a single kind of edge. Uh, we use many different kind of edge devices. Some are sophisticated, some are not so sophisticated. If they're environmental sensors, they might be resource constrained. If they're different, depending upon what kind of application that is supported, you can use drones, you can use AR, VR headsets, you can use gateway devices like Raspberry Pi, Jetson Nano. So you have a variety of devices in terms of their sensing, compute, and communication capabilities at the edge. So we know that this edge system is not trusted. So we call it an untrusted edge system. And why it's not untrusted? Because of numerous vulnerabilities that are present on the network. So any sort of communication within the edge or from the edge to the cloud is exposed to many different kind of man-in-the-middle attacks and other different kind of networking attacks. The literature is full of them. And so even though the edge is multimodal and diverse, it can be attacked through network vulnerabilities, and these vulnerabilities can further increase the effects of the delay-prone architecture that we have over here, um, and increase possibilities of different kind of attacks. Now, how do these network vulnerabilities impact time, and what kind of attacks it can launch on timing and degrade the perception of time for a given application? And then later on, we'll see what kind of applications are impacted by those time attacks. There are many different kind of vulnerabilities in time. By that I mean that any adversary that is present on the network can cause different kind of attacks to the different processes of time. For example, the transfer of time, the keeping of time, and those adversaries can add malicious delays. They can make the rate of time advance pretty inconsistent so that you do not have a good notion of measuring execution time. It can also induce drift, which is the rate of change of time advance that gets accumulated over time and can cause time discontinuities. So as a consequence, you have time discontinuities, which means that you'll have a sudden jump in time. And we all know what a sudden jump in time can do to many applications. And then it could also be fuzzy time, which means sometimes for a similar duration that has elapsed, our systems will report a lesser time execution or a greater time execution compared to what it normally is. So these are different causes due to network adversaries through which they can induce timing issues, and the consequences are time jumps and time fuzziness in time. Um, an attacker over the network can use different attack strategies to manipulate the sense of time. So let's take an example over here. You have a time source, and then you have an absolute reference time. We know that there's always a reference through which we measure time. And in a no attack scenario, their time perfectly matches the time source that you're interested in as compared to the reference time. But then if you induce time jumps arbitrarily, this is what happens. The time source would have a different sense of time with respect to the reference. And this kind of attack on time is called offset manipulation. You only jump time here. The other attack strategy would be increase the rate at which time advances. And then it is rate manipulation that the attacker can do. And if it's only done on a single time source, then it looks something like this. Over time, the error in time gets accumulated from the reference time simply by increasing the frequency at which the time advances. If we see the same attack on two devices, then the relative time between those devices um, also accumulates um, over here. So over here, we have decreased the time advance raised for the time source one, and we have increased the time advance raised for time source two. If one is slower and the other is faster, then their clocks drift apart from each other, and the time error accumulates more and more the more time that has passed. So you see that there are two different kind of attack strategies, the offset manipulation and the rate manipulation. And these two different kind of attacks have many consequences on real world applications that span the edge. So in one of the first few slides, I've shown how the networked edge architecture looks like. So all of these applications map to that edge architecture. You can have through these kind of attack strategies of rate manipulation, offset manipulation, you can misclassify activities in edge deployments where the distributed sensing devices, they need to sense the environment and sense the human activity and classify it accordingly. If we do not align their time well, and if we carefully manipulate their rate and offset, then we can stealthily misclassify an activity in a way that cannot be captured through any filters or sanity check that are provided in the algorithm. Similar for location, for different um, driver assistance applications, the timing attack can make the driver system believe that the um, owner is near, where in reality it's pretty far. So this kind of location-based attacks are pretty common that are anchored through time-based attacks. So if one of the attack that has been pretty famous, that if in autonomous cars, that if the autonomous car used a variety of distributed sensors on the device to estimate the distance between itself and some of the surrounding objects to apply brakes on time. If the timing attack that I just explained, based on that, the objects that are near may seem far, or the objects that seem far may seem near. And so the effects of that might be very catastrophic on autonomous systems. There are other safety critical applications like the grid. And with the smart grid, there are many sensors that are deployed that need to sense the health of the grid and act accordingly. And so it has also been shown in the literature that these timing attacks can force a part of the grid to completely shut down, even though there is no fault over there. And so all of these attacks are possible in a variety of edge applications. Some are safety critical, some are not so safety critical, but they all have negative consequences. So this is one of the attack that we have simulated on a Carla simulator on an autonomous system. And we launched a network time delay attack, which was a very simple. We add just a small enough of a delay at every new reading. And then the distance estimation went pretty wrong, and the car almost crashed on the side. We also tried to launch timing attack on the so-called trusted time that is present on trusted execution technologies. If you're aware of trusted execution technologies, ARM trust zone is mostly used for edge devices, and Intel SGX is mostly used for cloud devices. The idea over there is that the processor is completely secure from privileged adversaries. So we did an experiment where we show that the most commonly used trusted execution environment for the edge, which is ARM Trust Zone, does not provide a trusted sense of time. So even that time can be attacked. So if you see the graph on the left, we are launching different kind of delay attacks. And when we say constant delay, incremental delay, random incremental delay, we are inducing very small enough of a delays that are not noticeable by the system. And then over time, the error gets accumulated. So if you see that when the true time was almost 3000, the time error, it's pretty large for random incremental delays. And for incremental delays, it has accumulated to a larger amount. And the consequence of those accumulated time errors we have shown on accuracy degradation of multimodal machine learning models. So multimodal machine learning models are trained for activity classification, activity recognition of humans. And so we've shown that if you keep on increasing the time error, the accuracy of your machine learning model keeps on decreasing, and then it also decreases beyond a certain threshold. Um, so this is what we have simulated over real edge devices that are carrying an arm trust zone by simply manipulating the time by adding very small delays over longer periods of time. So before I go into my problem, I mean, um, formalizing the problem and explaining the proposed approach, does anybody have any questions on the motivation of time security? If not, can you still hear me?
Sorry, what happened here?
No, nothing. I'm just doing a sanity check if I'm still there, if
Yeah,
everybody's
yeah,
still
no,
there,
no,
and
you're
if
there.
anyone has a question.
Yeah. And in
Okay.
addition to like everyone, you can unmute and ask questions. You can also use the chat for those who don't have.
I cannot, somehow on my system, I cannot access chat while I'm presenting. So,
Yeah,
Ahmad,
I mean,
if you
I can
can
take from the
take a
chat.
look at the chat.
Yeah, yeah.
Yes, and
I'll
feel
take
free
care
to
of
interrupt me anytime. I
it.
know
Sure.
it's hard to remember your question till the very end of the presentation.
Yes.
Okay. So that was it about the motivation, which is what kind of timing attacks are possible, what kind of consequences they have. And I've shown some of our own implementations of timing attacks and their consequences on real applications. This one was on an autonomous car, and this one is on activity recognition, where we launched the attacks on the machine learning models. Okay, so this is where we have formalized the problem and the proposed approach. On the very left side is what the problem is. The problem is that there are privileged adversaries on the network and they compromise all components of a time stack. Now, what's a time stack? Time stack has a hardware component, which is oscillators. And in the literature, it has been shown that attacks are possible on the counts that are generated from the hardware oscillator. The attacker can increase the frequency or decrease the frequency through the DVFS, dynamic voltage and frequency scaling mechanism, and change this count value that come out of the hardware counters. Then another attack is possible on the software through a privileged OS adversary if you cannot trust them. And then finally, this is the local sense of time. And then once you want to synchronize your time to global time, then there are many adversaries on the network that compromise time as well. There are many men in the middle attack that drop packets, delay packets, force packets. There are numerous attacks that are possible over there and reported in the literature. So this is a problem. We have attackers that can attack times at different levels of the stack. Now, if we would like to secure this entire time stack, then we have to secure every layer of the time stack from the three broad categories of time attacks. And for that, we have proposed an approach that is divided in three tasks. Our very first task, it is responsible for overcoming these attacks one and two, and its job is to maintain a secure sense of local time. It is not protecting against global time attacks. So we call these processor clocks because if we secure the clocks of the processor, then we are securing the local time. And we have a detailed mechanism to do so, and I'm not going to detail of this particular task. Our second task is about sensor clocks, and it is going to overcome the attacks on global time, which happens on the network. So if you're familiar with time synchronization protocols, the fundamental idea behind time synchronization protocols is to exchange timing packets over the network, which is time transfer over the network. That is the fundamental idea behind, you know, tens and twenties of synchronization protocols that are out there. We would like, and there are many attacks that are possible on time on the network. And network is vulnerable to a lot of timing attacks. We are very much aware of that as well. So what we are doing is trying to see if we can explore alternative um, time transfer mediums beside the, instead of using networking mediums, why not use sensing mediums and see if we can design time synchronization protocol, not on networking medium, but on sensing medium. And we use different kind of approaches like that are traditionally used for networking channels and see what sort of challenges we have when we apply those approaches to sensing channels. And then finally, our final task is about network clocks, which is it's impossible to eliminate the use of networking channels for all applications and for all technologies that are out there, particularly for long range communication. You definitely have to rely on networking because with sensing, you are confined to short spaces. And so we also talk about long range networking clocks and how to overcome the attacks or decrease the effect of the attacks on long range networking technologies, and we call that network clocks. And our focus has mostly been on 5G technologies in that area. And in order to provide a secure time across these three stacks that are tackling these attacks on the entire timing stacks, we make sure that our time is secure, it's precise, it's resource efficient. We do not want to burn a lot of resource to provide that kind of time security. It's delay tolerant and it's extensible. And by extensible, we mean that that our solutions are applicable to a wide variety of applications and not just specific to a single hardware and software and an application. Okay, so we do not have time to go into details of every task, and we still have ongoing work for these different kind of tasks. The work has not is not complete as of yet, and so I am going to briefly talk about sensor clocks, which is how would you synchronize time over sensing channels? And why are we considering sensing channels and not networking channels? Because networking channels are full of attacks, timing attacks. Whereas since it's very hard to launch the two kind of attack strategies I mentioned, like rate manipulation, offset manipulation on sensing channels, particularly when the sensing channel is very diverse. Because there's just not only one kind of sensor, and many different kind of sensors. They use very different technologies out there, and so crafting these attacks on these individual sensor technologies is not trivial. And so that's why we're considering the sensing channel and see what kind of potential it has for secure time sync. Okay, let's go into detail of sensing channel. Before we go into that, our goal is that we want to make a case for sensing channels for time sync. And we would like to show it over heterogeneous commercial off-the-shelf devices because that's how our edge is right now. Our edge devices are pretty diverse. They have very diverse sensing capabilities, very diverse networking capabilities. They're mostly off-the-shelf devices that are combined together to provide extensible deployments, which require very less manual calibration, and they would work, and they are very scalable in nature. And they're resource constrained, and so the goal is also to devise solutions that do not consume a lot of bandwidth and computational cost. And so we'd like to see these alternative signals, which is the sensor signals, and the channels, which are the sensing channels for time sync. So that's the goal of this task. There has been prior work that looks into sensing for synchronization. If some of you recall that electromagnetic waves are used that are generated from our power line signals have been harvested by um, tiny embedded and edge devices to extract timing information. Similarly, the fluorescent lights that are also driven by the power line signal have periodic time signatures, and uh, properly designed edge devices have captured those fluorescent lights and extracted timing information from them. And so, of course, they do not rely on networking channels, so they are not susceptible to the timing attacks that are present on the network. And they can have any kind of radio, and it doesn't matter. They can still synchronize with each other because they rely on sensing and they consume less power. But they also have limitations. For example, they use customized hardware, which means the solutions are not scalable and extensible. They use very specific customized hardware frontends and signal processing techniques to extract time information, and they do not support diverse sensors, which means if a technique is developed for one kind of sensor, it will only be used for that kind of sensor and not for other kind of sensors. So these tools are pretty rigid to particular hardware functionalities of the hardware devices. So they're not extensible in nature, and they cannot be extended to commercial off-the-shelf devices that we can just get and scale our solution. And so this lack of support for commodity sensors is what hinders the adoption for these kind of approaches to general edge deployments. So the problem over here is that we want to develop a universal sensing based time sync and not a sensing based time sync that is used for a single kind of hardware. No matter what kind of software, network, or radio support the hardware has, the solution should work. And it should be resource efficient, which means it should consume less power, bandwidth, and computational requirements so that it can work on those off the shelf devices. There are two kind of sensing approaches we could use. One is active sensing and the other is passive sensing. So in active sensing, different kind of sensor, for example, the most prevalent sensors that we can find on off-the-shelf edge devices are audio, microphone, light, optical is light. And so if we can do active light communication through optical sensor, active audio communication through microphone. We will be able to provide active sensing channels that can transmit the timing information from the transmitter to the receiver. And within that sensing signal, they can modulate the timing information on top of it that they extract from the grid to synchronize their time. So this is one approach that we use, and I'm not going to go into detail of that approach. The other approach that we use is passive sensing, which is much more resource efficient because over here, the devices who need to synchronize with each other, they passively sense the activity in the environment instead of actively transmitting and receiving sensing signals. So in this example, they passively sense human activity or machine activity or any other activity in the environment. So over here, if the human is in the environment and they close the door, then the sound from door closing is captured by microphone, the light change of door closing is captured by optical sensor, and the vibration from door close is captured by the IMU sensor. And since all of those devices capture these events at the same time, they can timestamp the event and correlate the timestamp with each other to synchronize with each other. So this is the passive sensing approach and the high level idea. And I'm going to go into a little bit of detail of this approach given the time that we have. So what we do is we harvest ambient events to synchronize time across heterogeneous IoT devices. That's the key line for passive sensing. And if you see over here that when the door opened and the door closed, the different kind of sensors, the top is microphone, this is IMU, this is optical, they all captured their respective events at the same time and timestamp them. And so if you plot the signal and then if you timestamp when the event has occurred and you correlate the timestamps, you can find the offset between the timestamp and correct the times for these devices. So in theory, it looks simple enough that you can detect the event, timestamp the event, then correlate the event and find the offset and drift between different devices. But in these individual steps are pretty challenging, which is how would you detect the event in a robust manner across all of these sensors? Then how would you timestamp precisely uh, the right edge of the event, then how would you later on correlate event across all of these sensors? So these are the three challenges that we address. One is the event detection, and event detection is a hard problem in sensor networks. It consumes a lot of resources, especially when the sensors are sampling the data at a high enough of a rate. There is an approach in the literature called cadence. Its throughput is 33 samples per second, and it uses a dedicated GPU to process those 33 samples per second. Whereas the sensors that we are talking about, particularly audio sensor, they produce events in the order of kilohertz. And so we want a throughput of kilohertz, and we want our approach to be lightweight and at the same time. And we want it to be universal, which means whatever event detection approach we choose for one sensor should work across all sensors. And then we do not require any manual calibration so that we can scale the solution across different kind of sensors. So this is one problem. How would we detect an event that's lightweight, universal, and scalable? And then once we are able to detect an event, how can we overcome the problem of delays that occur among common events across different devices? Because devices are at different distances with respect to each other, their corresponding sensing signals propagate at a different speed from the source to the sensor. And so they will not necessarily arrive at the sensors at the same time due to different distances and different propagation speeds. So how do we overcome those kind of delays in our time sync? And then finally, we can definitely synchronize two devices, two sensing devices with each other, but how can we achieve a network-wide sync where there are hundreds of sensing devices that are deployed all across a space, and they may not necessarily be close to each other, maybe far from each other. So how can we achieve a network-wide sync? So tackling the very first challenge, which is how do we detect event? We rely on the intuition that sensor data in their mostly have sensing data distribution, and anytime an event occur, they deviate from that distribution. So if we're able to train an encoder um, based on a particular sensor distribution, we can use that encoder to estimate the distance between the normal sensing distribution and the distribution that we get once an event has occurred, and calculate the distance. And whenever there is a sudden change in distance and we have a local maxima or a minima, we are able to detect the event. So the sensor data distribution is fed to an autoencoder, and the autoencoder is trained, and then that is used to calculate distance scores. And based on distance scores, we're able to see if an event has occurred or not. So this is how our pipeline looks like. And our solution is pretty scalable because we're using autoencoders that use unsupervised learning. And so we do not need any kind of manual calibration for different kind of sensor data. All we have to do is train an encoder for every sensor. But that is also a very tedious task to train an encoder for every sensor. And another issue is that encoders use 32-bit floating point matrix for training different layers of the encoder, which is also a very compute intensive task, which our sensor devices cannot handle. So we have proposed a quantization approach, and we use 8-bit integers to overcome the heavy computation. We definitely lose accuracy in that process, but in order to avoid that, we use in order to make our solution lightweight and universal, we use a unified encoder, which is trained on all different kind of sensors. And then to further fine tune the performance, we've trained specialized encoders for that particular sensor, but those encoders only have single layers. And so training those would not be much of a compute intensive task. So coming back here, we also would like to tackle high data rates. So in order to tackle high data rates, what we do is that we do the previous pipeline on a downsampled sensor data, but once an event is detected, we took the raw data, which is a high enough of a data rate, and only apply our event detection on that window to get fine-tuned timestamp measurement for that particular event detection. So instead of trying to detect events at those points when the event has not occurred and wasting too much computational power on it, we do not spend too much computation over there by downsampling the data, and then only spend that much compute when an event is detected. We spend that compute on locating the exact timestamp of that event. And so we call this approach cascaded detection approach. And so that's how we tackle high data rates of sensors, particularly audio sensors that operate in the range of kilohertz. And so this is how everything comes together. We have different kind of sensor data that is fed to a unified encoder. From there, it is fed to specialized encoder. And these are quantized models, both kind of encoders. From the encoders, we calculate the distance. And from the distance, we know that if the event has occurred or not. And we present the events from all of those different kind of sensors. So that was how we detected the event and how we overcome the challenges in event detection. Now we'll see how do we overcome our second research challenge, which is overcome the variable delays, variable propagation delays across two different kind of sensors that need to synchronize with each other, but they are present at different distances, and they have different sensors that have different propagation. Their sensing signals have different propagation speed. So if you calculate an optical sensor delay in this scenario and an audio sensor delay, you would see that the delay is impacted by the distance at which they are from the event, and also the rate at which the sensing signal propagates for that particular technology. So we know that light propagates faster than audio, and so that would impact the delay. And so how do we overcome these delays in our clock sync mechanism, because these delays can accumulate to large errors in the synchronization process. So what we noticed in our empirical experiments that for one kind of activity and for one kind of sensing pair, most of the propagation delay is present. The difference in propagation delay is present, but it gets accumulated over a particular value. And so what we have deduced that the propagation delay or the change in propagation delay across two different kind of sensors for one particular activity is constant, no matter how many times you try it. And so we have done these experiments for different activities and for different sensing pairs, and we've we've estimated the change in propagation delay for different kind of sensing pairs, and we've used it um, to adjust our clock synchronization and to overcome these kind of delays. And we ran a few experiments using different kind of devices and different kind of activities. And I'd like to talk about some of the results and some of the key takeaways from those results. If you see the left-hand figure where we plot a drift plot for different device pairs, we use SDK. SDK is one kind of sensing device. ESP is another kind of sensing device. They use different kind of sensors, different kind of network technology. They are completely different devices. And then we also see the drift estimation of SDK to ESP. So what we have seen, this is ground truth, and these are different frequencies of the devices that we used. So our key takeaway from this result is that devices with higher sampling frequency yield better clock estimates. So you see that this is the best estimate, which is operating at 200 hertz. This is the best estimate, which is 200 hertz, the maximum frequency. So we did similar experiments on same devices, but with different sensors now. So this is for the same kind of sensor with different sampling frequency. But the next plot is with different kind of sensors at the same frequency. And over there, our key takeaway is that some sensor types at the same frequency on the same device perform better than the others. So over here, the best estimate is in the audio and optical sensor that we get over here. And then finally, this result is that the more events the devices, the more common events the device observe, the better error they have. And so this inverse relationship is pretty intuitive, and it's pretty analogous to network-based time synchronization as well, that in networking, the more often you exchange packets, the better synchronization accuracy you have. And over here, the more sensing events you observe, the better error estimate you have. So the final challenge is, how would you achieve network-wide sync? So we have these complex sensor networks, and we want to synchronize every device with every other device in the network. What we've done is we've provided a clustering approach, and then after that, we prune the extra edges among devices such that there is only one edge across two devices. We do not want one device to synchronize with every other device through our proposed approach, because it's a very tedious task and it does not provide any kind of benefits. So instead, we find the right sensing pairs that synchronize with each other, and through transitive property, the entire network would be synchronized with each other. And so overall, this is how our design looked like. We have a bootstrapping phase where we have a sensor network. We collect data, we train encoders, and once we have trained the encoders, we have a mutual event count, and we prune a sensor network and find the right sensing pairs. This is the bootstrapping phase. And in the synchronization phase, we get the data only from the sensing pairs that should sync with each other, and then we stream the data through the encoder we have trained that detects the events, and the timestamp for those detected events are used to estimate the clock parameter, which is offset and drift. This is how the entire system comes together for sensing-based synchronization. So we've done evaluation on different kind of devices with very different capabilities, with very different kind of sensors, um, and we've estimated them, and we've changed the frequency, sampling rate, sensor type, and saw their effect on clock drift. And then finally, we did real deployments on smart homes and wireless body area networks to evaluate our approach, and also evaluate our network-wide synchronization and see what kind of results we get. And we've also compared our approach with NTP, which is the only other universal sync approach in the networking domain. So in the interest of time, I'll only show the smart home case study. I'll not go into detail of anything much because I'd like to leave the last 10 minutes for questions. So this is how we deployed our different devices, and we've used different devices with different sampling frequencies and different sensing modalities. And in our results, we saw the synchronization error for the devices that are near to each other, and also devices that are far away from each other and that did not synchronize with each other through our approach. Instead, they got transitively synchronized with each other through multiple hops of other devices. And so the devices that are directly connected with each other, we achieve an average error of a few milliseconds, and at best, we were also able to achieve under a millisecond. And then for devices that are not, that are multiple hops away from each other, of course, the errors were greater than when the devices were directly connected to each other, but errors still in the range of a few milliseconds. And we also compared our approach with NTP. And with NTP, we're consuming 36% of less power. And the key result is that we achieve better mean error and spread than NTP. When NTP was connected using serial and BLE connection, while we were also consuming less power. Okay, so coming back to the main proposed approach where we chose to only talk about sensor clocks. So there's definitely the key takeaway from this is, and this is still an ongoing work, we're still exploring other properties of sensing channels, both active and passive sensing. And the key takeaway over here is that there's definitely potential for sensor clocks for secure time sync, because there are lesser attacks that are possible over here that are dominant in the networking domain. But then also, we try to overcome attacks on local clocks through our dynamic memory protection, integrity protected clock sources, and some time verification mechanisms. And we also develop delay tolerant and fault tolerant time synchronization approaches for the long range networking mediums such as 5G. And so with this, I'd like to finish off my work. All of these directions are still ongoing. And if anyone has an interest in any of these directions, feel free to email me. My email address has been provided on the very first slide. And with that, I'd leave the rest of the time for questions. So you can use the chat for questions or just directly unmute yourself and ask the question.
So maybe I have a question. Thanks for the interesting talk. I was wondering whether you also are looking into combining multiple sensing channels to gain some fault tolerance and not
Right.
to increase the attack surface at the node.
You're right. Yes. In a way, we are doing it um, because let's suppose we have one device, and most of these devices do not have just one sensor. They have multiple sensors. For example, we used an ESP32 Things device. It has audio, it has IMU, and if it doesn't, there are many applications that require them to have it, and the external sensors are also interfaced. So instead of just choosing IMU to synchronize, or instead of just choosing the audio sensor on that particular device to synchronize, you can choose to synchronize using all of the sensors. Of course, it's tedious. Now, it all depends on what your goals are. If you fear attack on one channel, you can use multiple channels and then overcome the attack. And but if the goal is performance and lesser resource consumption, then you can choose the best of all and just use that for synchronization. So it all depends on what the goals are.
Thanks. In a similar direction, I also had a question. Could you maybe explain again why do you prune down the network graph to only single connections to neighbors? I would have guessed that having multiple connections would also increase fault tolerance there. Is there
You're
also
right.
the
Yes.
efficiency argument that you are
Yeah.
pruning it
Yes.
down? Okay.
The
So it's
yeah, the
kind of
answer
a
is the same.
trade-off. Yeah, okay, yeah.
Yes.
Thanks a lot.
Yeah.
Yeah,
Our major goal was resource over here. But if it's fault tolerance, or if we know that the attacks are possible on the other channels, then we do not need to prune it.
I see. Yeah, yeah, that makes sense. Thanks a lot.
Yeah. Thanks for asking.
Any more questions? Just wondering about the IMU. Is that IMU also like precisely like time stamped, like the events you get from IMU or not?
It all depends on what the sampling frequency is. So we're bound by sampling frequency. We cannot do better than that. So if it's only a few hundred hertz, then that's the best you could do. And it also depends on the kind of software stack they have and what kind of time stamping capability they provide, what kind of delays you have over there. So what we do is whatever device we want to work with, we see what's the best time stamping we can get out of it, and we just work with it. So the audio time stamping accuracy is better than
Yes.
IMU and optical. Optical is the worst in terms of the software delays and the stack delays that you have over there.
Can't we have like some hardware ways to take care of that? Let's say, for example,
I
you have a direct channel of, let's say, some threshold comparison, like
um Yeah, anything is possible as long as we know what our goal is. So our goal over here was scalability.
I see.
Just use off-the-shelf devices and make them work with the approach. But if our goal is higher accuracy, higher precision, we can come up with techniques through which we can extract um, accurate timestamps from these different sensing devices.
Yes.
We can try to find ways.
Mhm.
And that has been done in previous sensing approaches, which is in order to get very good time with less noise, they've produced their own hardware front ends. And
Yeah.
so over there, our argument is that it's not scalable and
Yeah.
it's only fixed for that sensor. And so it
Mhm.
depends what your design goals are.
Mhm. Any more questions from the audience?
Maybe I have one more,
Yeah, go ahead.
if we
Sure.
have time for that.
Yes, yes,
Yeah,
for sure.
Yeah.
because there was this comparison with NTP over Bluetooth. And in this context, I was asking myself whether it would make sense because we don't actually need Bluetooth to do this
Yeah.
message exchange for an offset measurement. Did you also look into how to, if you do away with the entire Bluetooth stack and only do offset measurements, maybe with a very simple protocol over the physical layer that is provided by these radios?
Yeah. Good question. The kind of deployment which we targeted and the kind of devices which we were interested in, the sensor network resource constrained devices, they do not have internet. So the only internet connectivity they have is via gateway. In our case, it could be Raspberry Pi, it could be other device. So these devices, what are the different channels through which they can communicate with the Raspberry Pi? Let's take an example of LoRa and ESP. LoRa is a very small resource constrained device, does not have internet. It can only communicate with Raspberry Pi through a serial connection. Whereas ESP, it can communicate through Bluetooth and it can also communicate by serial. Any device can communicate with serial as long as it has that wired connectivity. And so these are the kind of deployments that we have. Either they have some kind of wireless channel with the gateway or some kind of wired channel with the gateway. That's why we did one wired serial and one wireless, which is Bluetooth, because they do not have internet that they can run the NTP on their own. They can run the NTP through Raspberry Pi, through the gateway. And so that's the kind of setup which we have. And so if they're doing it through Raspberry Pi and then the internet and then running the regular NTP protocol, it has those extra propagation delays that are directly proportional to the kind of technology they're using for communication. With serial, you'll have less delays. With BLE, you will have more delays. For some devices, the constraint is they cannot run a wire from the device to the gateway. They need to be wireless. And over there, you'll have much more um, uncertainty in the propagation delays. So did this answer your question? That was the kind of deployment we were targeting. There was just no way we could run NTP on those devices directly.
Yeah, maybe my question was a little bit more specific in the case where you do Bluetooth-based synchronization.
Mhm.
There, I was asking myself whether it is necessary to have the entire Bluetooth stack running, but instead
Oh, I
just
see.
take the radio that is
Mhm.
providing the Bluetooth functionality, then
Okay.
but then do away with the entire Bluetooth stack, which also adds some complexity and energy consumption,
Yeah.
and do a much simpler protocol just on the physical layer, basically between uh, the edge device and maybe a gateway device that is supporting this kind of
Okay. Okay. Now I
radio
get your question.
technology. Yeah.
Um, so definitely the physical layer based optimized solution might work well. It can reduce those uncertainty in the propagation. But in our deployment and in most cases how the developers deploy or communicate using BLE, we've used that. We did not use any physical layer mechanism because then that requires extra tweaking. And I'm not so sure how much you have to go down in the hardware to, and what kind of changes do you have to make in order to make that possible and reduce the time propagation uncertainty in the Bluetooth stack. But if you just use it as it
Yeah,
is,
yeah.
as it is, of course, the propagation delay is highly asymmetric. There's much more uncertainty. Did this answer your question?
Yeah, yeah, thanks.
All right. Any more questions? We're on top of the hour, and hearing none, then I would like to thank Dr. Anwar for the informative presentation, and wish everyone great rest of the week, and see you guys in 2 weeks.
Thank you.
All
Thank you for
right.
organizing and inviting and
You're
all the
welcome.
questions.
You're
Okay,
welcome.
bye.
All right. Bye, everyone.
See you. Bye.
Thank you.